The last part of Unit 5, Notes 5.3, deal with molecular polarity and solubility. So, molecular polarity. First of all, what we want to recognize is that molecular polarity, or the polarity of an entire molecule, is determined by symmetry. Okay, so we are going to be looking at the overall shape of the molecule and deciding is the molecule symmetrical or asymmetrical to decide if the molecule is polar or nonpolar. Okay, in the past, we have talked about polar and nonpolar bonds, and recall polar and nonpolar bonds were determined based on the difference in electronegativity. But when we talk about the molecule as a whole, the polarity of an entire molecule is going to be determined by the symmetry. Okay, is it symmetrical or not? Polar molecules, then, are molecules that are asymmetrical. Okay, so this prefix A here means without. So essentially we are talking about molecules that do not have symmetry or are not symmetrical. Okay, sometimes it can be difficult, especially in 2D, when we draw these pictures, to decide if a molecule is symmetrical or not. And so what we really want to take a look at is the lone pairs of electrons. Okay, so most polar molecules are going to have at least one lone pair of electrons, and I should clarify here, that are found on the central atom. Okay, so the atom at the center of our molecule. If there is a pair of lone pairs on that electron or on that atom, then usually that's a good indication that we are dealing with a polar molecule. Okay, it is important to note that polar molecules could have nonpolar bonds. So if we looked at the difference in electronegativity, the difference could be small enough that they are sharing the electrons equally, therefore they have nonpolar bonds. However, the overall polarity can be polar based on the symmetry. Okay, so an example of a very common polar molecule is H2O. If I were to draw, and hopefully we're getting pretty good at Lewis structures for H2O, we would end up with a molecule that looks like this. Okay, once again, when I look at this, it is going to appear as though maybe it's a symmetrical molecule because it's drawn in the 2D. However, if I were to look at it in the 3D, we would see that the shape changes a little. And so what we're really looking at here are the presence of those lone pairs. And we have a pair of lone pairs here and a pair of lone pairs here. And so this is going to be an asymmetrical molecule or a polar molecule. Okay, so polar molecules are asymmetrical, and most of them are going to have at least one lone pair of electrons on that central atom. Nonpolar molecules, then, are going to be molecules which are symmetrical, meaning if we were to look at the central atom, if we were going to cut it any way, whether it's down the x, y, or z axis, both sides of that molecule would be the same. Okay, once again, sometimes this can be hard to see, especially in the 2D. So we're going to once again focus on this idea of lone pairs of electrons, and nonpolar molecules do not contain lone pairs of electrons on the central atom. And just a side note, most nonpolar molecules are also going to have nonpolar bonds. Okay, so a very common nonpolar molecule is carbon dioxide. We talked about this. This is a molecule that's going to have some double bonds. And so if I were to draw the Lewis structure for carbon dioxide, I would end up with this. Okay, once again, we're focusing in on that central atom, and this carbon has two bonds on each side coming out of it for a total of 4 bonds. There are no lone pairs on the central atom, and so therefore we would classify CO2 as a nonpolar molecule. Okay, let's do 2 more examples. Let's say we wanted to draw CCl4. Okay, if we draw CCl4, our Lewis structure is going to look like this. We're going to fill in my electrons. Okay, and when I take a look at my central atom, there are no lone pairs on the central atom. This is a symmetrical molecule, and so CCl4 would be classified as nonpolar. Okay, if I were to draw NH3, I would see NH3 looks like this. Okay, NH3 does indeed have a set of lone pairs on that central atom, and therefore it is asymmetrical, and so this is going to be a polar molecule. So again, if you can properly draw the Lewis structure, determining if it's polar or nonpolar isn't all that difficult. We're just focusing in on that central atom and are there lone pairs or not. Okay, so why is this important? Well, the shape of a molecule, the polarity of a molecule is important because it can help us determine some of the properties of the various atoms. And we can see that on this slide, we have a polar and a nonpolar molecule, so we would expect these two substances to not mix. Okay, water and CCl4 would not mix with one another. Or of the molecules, I should say. And so one of those properties we're going to look at is this idea of solubility. Okay, by definition, solubility is the ability of a substance to dissolve in a solvent. Okay, so sometimes when we talk about if something is soluble or not, we're talking about can a solid dissolve in a liquid. Okay, so a solvent is going to be any liquid. If we think about Kool-Aid, Kool-Aid is soluble in water, right? We take a Kool-Aid packet, we dump some sugar in it, we add some water, we stir it all up, and it mixes evenly. Okay, similar to solubility is this idea of miscibility. Miscibility just has to do with two liquids that mix fully. So solubility, miscibility are sort of the same thing, except for the fact that one of them is typically referring to a solid dissolving in a liquid and the other is talking about two liquids that mix with one another. Okay, so the solubility rule that we really want to remember or understand is this phrase, like dissolves like. Okay, this has to do with the polarity of the molecule, and what the solubility rule, like dissolves like, says is that polar molecules are going to dissolve other polar molecules. Okay, nonpolar molecules will dissolve nonpolar molecules. However, polar molecules are not going to dissolve in nonpolar. So if you have two different polarities, one polar, one nonpolar, they are not going to mix. But two polar molecules will mix with one another, two nonpolar molecules will mix with one another. Okay, so that's what that like dissolves like means. Again, as a side note, ionic compounds typically dissolve in polar molecules. Okay, so I might ask you something if we go back to this